Hello, this is Team 7 and we will be discussing turbo machines. First, I would like to briefly introduce what turbo machines are. Turbo machines are dynamic fluid machines that add or extract flow energy from a fluid. Pumps add energy to a fluid and turbines extract energy from a fluid. Fluid and mechanical energy are exchanged using blades mounted on a rotor. A fluid that is moving can force rotation and produce shaft power, or we can exert shaft torque and force the fluid to move. There are three classifications of turbo machines: axial flow, mixed flow, and radial flow. For an axial flow machine, the fluid maintains a significant axial flow component from the inlet to the outlet of the rotor. For a radial flow machine, the flow across the blades involves a substantial radial flow component at the rotor inlet, exit, or both. In other machines, designated as mixed flow machines, there may be significant radial and axial flow velocity components for the flow through the rotor row. On the right-hand side of the slide, there are two examples. The top one is a radial flow machine, and the bottom one is an axial flow machine. Let's talk about some basic energy considerations for turbo machines. An understanding of the work transfer in turbo machines can be obtained by considering the basic operation of a household fan and a windmill. A fan is an example of a pump, and a windmill is an example of a turbine. For pumps, the blades do work on the fluid, and for turbines, the fluid does work on the blades. Although flow inside a turbo machine is complex, the essential phenomena can be illustrated by use of simplified flow considerations and velocity diagrams. The actual fluid velocity V can be denoted as the vector sum of the relative velocity W and the blade velocity U. The figure on the right represents idealized flow through a fan. The image displays a cross-section of the fan blade with velocity diagrams showing the absolute velocity, relative velocity, and blade velocity at the inlet and exit of the fan blade section. The key takeaway from this sketch is that the fan blade pushes the fluid, causing it to change direction. The absolute velocity vector is turned during its flow across the blade from section 1 to section 2. Initially, the fluid had no component of absolute velocity in the tangential direction. When the fluid leaves the blade, this tangential component of absolute velocity is non-zero. For this to occur, the blade must push on the fluid in the tangential direction. That is, the blade exerts a tangential force on the fluid in the direction of motion of the blade. Because the tangential force and the blade motion are in the same direction, the blade does work on the fluid, and this device is a pump. Conversely, when the tangential force and blade motion are not in the same direction, the fluid does work on the blade, and that device would be considered a turbine. Angular momentum considerations. Since all turbo machines involve the rotation of a rotor about a central axis, it is appropriate to discuss their performance in terms of torque and angular momentum. If shaft torque and rotation are in the same direction, it's a pump and shaft torque is positive. Otherwise, it's a turbine and shaft torque is negative. The amount of shaft torque can be calculated from the moment of momentum equation for a control volume. Looking at the equation for shaft torque, we can see that the shaft torque is directly proportional to the mass flow rate. It takes considerably more torque and power to pump water than to pump air with the same volume flow rate. This is due to the differences in mass and therefore mass flow rate between the water and air. The greater the mass flow rate, and the larger the shaft torque will be. The equation for shaft torque is also called the Euler turbo machine equation. The Euler turbo machine equation is derived from the axial component of the moment of momentum equation. We can multiply both sides of the Euler turbo machine equation by angular velocity to get it in terms of shaft power or shaft work. If we want the work per unit mass, we simply divide the shaft work by the mass flow rate. Work per unit mass can also be written in terms of inlet and outlet velocities. We can see here that the work per unit mass is related to the changes in the absolute, relative, and blade velocities. One of the most common radial flow turbomachines is the centrifugal pump. The centrifugal pump has two main components, the impeller and the housing. The impeller consists of blades that are usually curved, arranged in a regular pattern around the rotating shaft. The housing is a stationary casing enclosing the impeller. As the impeller rotates, fluid is sucked in through the eye of the casing and flows radially outward. Energy is added to the fluid by the rotating blades, and both pressure and absolute velocity are increased as the fluid flows from the eye to the periphery of the blades. The image on the right shows the basic elements of a centrifugal pump. The basic theory of operation of a centrifugal pump can be developed by considering the average one-dimensional flow of the fluid as it passes between the inlet and outlet sections of the rotating impeller. For incompressible steady flow in a pump, we can use the mechanical energy equation from Chapter 5 to write the work per unit mass equation in terms of pressure, velocity, and head. Head refers to the discharge pressure of the pump. I have included the equations for head, head loss, ideal head rise, and actual head rise. Due to the general complexity of flow through a centrifugal pump, the actual performance of the pump can not be accurately predicted on a completely theoretical basis. Actual pump performance is determined experimentally through tests on the pump. Some pump performance characteristics are power, horsepower, which is traditionally called water horsepower, and overall efficiency. Equations for calculating these performance characteristics are shown on this slide. The graph on the left shows the typical performance characteristics for a centrifugal pump of a given size operating at a constant impeller speed.
Okay, now we're going to talk about dimensionless parameters and similarity laws. Dimensional analysis is used to plan and execute experiments, as well as presenting the data. For example, the characteristics of a pump is usually determined experimentally, where it is expected that this analysis will be very useful to study and document such characteristics. The principal dependent pump variables are the actual head rise, shaft power, and efficiency, which depend on geometrical configurations and can be expressed as the equations on the left side shown here. The last term of each equation is a form of Reynolds number, which can be neglected when the flow has a high Reynolds number, and this is usually the case. The relative roughness can also be neglected in pumps, thus simplifying the previous equations to the ones on the right side on this slide. Pump scaling laws. When two similar pumps are operated at the same flow coefficient, we get the following equations shown on the right side of this slide. With these scaling laws, the characteristics of one pump can be experimentally determined. Then, using this data, we predict the characteristics of the other geometrically similar pumps. Now I'm going to talk about the special cases. There are two special cases and we can see the respective equations in this slide. The first one is when there is a speed change. Here we can see that for a pump operating with a certain flow coefficient, the flow varies directly with speed. The head varies as the speed is squared, and the power varies as the speed cubed. The second case is when the impeller diameter changes. Here we can see that for a pump operating at a certain speed and same flow coefficient, the flow varies as the diameter cubed, the head varies as the diameter squared, and the power varies as the diameter is raised to the 5th power. A specific speed and suction specific speed. In this slide, we can see the equations for each dimensionless parameter. First, we have Ns, which is the specific speed used to find the peak efficiency, and with this we can find an appropriate type of pump for a specific application. NSD is the same parameter but using the US customary units. We also have SS, which is the suction specific speed. It is used similarly to the specific speed, but to determine the operator conditions on the suction side of the pump, so the inlet side of the pump. SSD is the same parameter but using the US customary units. Now I will talk about axial flow and mixed flow pumps. Axial flow pumps are often called propeller pumps. This type of flow is in the actual direction, opposite to the radial flow for centrifugal pumps. The characteristics of these two types of flow are very different. At maximum efficiency, the head and brake horsepower are the same for both pumps, but as the flow rate decreases, the power input to the centrifugal pump falls, while for the axial pump it increases. In the axial flow pump, there will be a small flow rate change with a large head change, and in the centrifugal pump, there will be a small head change with a large flow rate change. This will be at a flat head curve. It is also important to know that to start a centrifugal pump, the system should be closed, whereas for the axial flow pump, the system should be wide open. In general, the efficiency of the axial pump is lower than that of the centrifugal pump, except for when they are at design capacity. Fans. They're also called blowers, boosters, and exhausters. It all depends on the location. Fans are usually used to move gas or vapor. They normally operate at low rotation speeds and are capable of moving large volumes of gas. When dealing with fans, gas density is treated as a constant, since it usually doesn't exceed the 7%. So, to produce larger changes in gas density, turbo machines called compressors are used instead of fans. Fan designs include centrifugal, mixed flow, and axial flow fans. They also have their own version of a specific speed, NSDF, which is determined by the equation that you see below. Now I'm going to talk about turbines. These devices extract energy from flowing fluids. The shaft power generated from this can drive generators or other devices. They are classified based on the mechanism of the fluid interaction with the blades. There are two types, impulse and reaction turbines. Both turbines can be analyzed using the moment of momentum principle. And in general, impulse turbines are devices with high head and low flow rate, whereas reaction turbines are devices with low head and high flow rate. Impulse turbines. In these machines, the total head of incoming fluid is converted into a large velocity head at the exit of the nozzle. The space surrounding the rotor is not completely filled with the fluid. There are many types of impulse turbines, but here we only focus on two. The first one is the Pelton wheel, which is essentially an improved water wheel with tangential flow. It is most efficient when operated with a large head. The second one is an axial flow device. It is used most often with air as the working fluid. But just like with the Pelton wheel, the inlet and exit pressures are equal, and the magnitude of relative velocity is unchanged as the fluid flows across the blade. In this type of turbine, the fluid does work on the blade. And finally, we have the reaction turbines. In this type of turbines, the working fluid fills the passageway completely. Pressure, velocity, and angular momentum of the fluid decrease as it flows through the rotor, which then extracts energy from the fluid. Similarly to pumps, turbines are designed with different configurations: radial flow, mixed flow, and axial flow types. It is necessary to determine which type of turbine will be best fit to do certain operations before detailed design work is done. Using the specific speed parameter NS can help to provide this information. For hydraulic turbines, the N prime S can be calculated by the equation shown here on the left. But the most common parameter used is the power specific speed, N prime SD, which is not dimensionless and can be calculated by the equation here on the right. Thank you for watching our video.